Section 7.1 in college algebra, we're going to discuss sequences and then also series. So let us begin with some definitions. A sequence. Your book probably has a very formal definition, but I'm going to give you a little less formal version. It's going to be a function with a domain of successive integers. Successive integers. So what that means is successive meaning one right after another, and integers meaning positive and negative whole numbers. And finite versus infinite is exactly what you think. A finite sequence will end, and infinite will not. And we'll see examples of these coming up. So our first sequence that we're going to look at is a sub n, which is notation for sequences. We don't use f of x or any sort of function notation because while these do look like functions, we're going to determine them to be sequences. The function, or I should say the sequence, the general term is 2n minus 1, and a sub 1 represents the first term. So if I were to find the first term of my sequence, I go to my formula for my sequence and I substitute in a value of 1 for n. So 2 times 1 minus 1 is a 1. The second term of the sequence would be if I take my general formula and I substitute in a 2 for the n. That'd be 4 minus 1, which is 3. And then my nth term, which is called the general term, is if I just leave it in general form. So 2 times n minus 1. And they want to know, is this a finite or infinite sequence? Technically, it's infinite, unless they give me some sort of bound, which they did not. They might say something like for all n between 1 to 100 or something like that. So number 2, list the first 7 terms of this sequence. This is a special sequence though. A sub 1 is equal to the number 1, so the first term is 1. A sub 2 is also the number 1, but then after that it follows a new pattern. And the pattern says every term for my n's greater than or equal to 3 are going to be defined as my a sub n minus 2 plus a sub n minus 1. What that means is 2 terms ago plus 1 term ago, and I'm going to add them together. So for instance, a sub 3 would be my second term, which is 1, plus my previous term before that, and a sub 2. A sub 4 would be my 2 previous terms before him, so 1 and 2. A sub 5 would be the 2 previous terms before him. 3 and 2 is 5. A sub 6 would be the 2 previous terms before him, so 5 and 3 is 8. And a sub 7 is 5 and 8, the 2 previous terms, which is 13. This is called a recursive sequence because it's going to use, the formula is defined in context of some of his preceding terms. And this is a very special recursive sequence. It's very famous. It's called the Fibonacci sequence. And I believe there's 2 C's in Fibonacci. It's Italian. There you go. There's something else in this unit, in this section, called summation notation. And it has the Greek letter sigma. That's a capital sigma. A series is an addition or sum of all the terms in a sequence. And we're going to learn about finite and infinite sequences eventually, but for now we're just going to do some finite sequences. So this says my terms, my general terms defined as k minus 1 over k, and we're going to sum all of our sequence terms when k equals 1 all the way up to k equals 5. So basically what you have to do is find what the sequence is when k equals 1, 2, 3, 4, and 5, and then add the numbers together. So let's expand this summation. If k is 1, I would do 1 minus 1, which is 0. 0 over 1 is 0. And I'm going to add that to my second term, which is when k equals 2. So 2 minus 1 is 1. 1 divided by 2 is 1/2. And then my third term would be when you substitute in a 3. So 3 minus 1 is 2. 2 over 3 is 2/3. And then my fourth term, I'm guessing you see a pattern, is 3/4. And my fifth term would be 4/5. And then I could technically add all those together to find the answer, but what they wanted is the expanded notation for this summation, and that is it. There's the expansion of it. The next example has the index, what we call these is the index starting at 0 going up to 5. So we're actually going to find the first 6 terms because 0 would be the original term. And just like in the previous problem, summation means we're going to add the terms together. So my first term, when I substitute in a k equals 0, negative 1 to the 0 power is 1. 2 times 0 plus 1 is 1. So I have 1 over 1, which is 1. Now my next term, if I substitute in k equals 1, I have negative 1 to the first power, which is negative 1. 2 times 1 plus 1 is 3. So I ended up with a negative 1 over a 3. Instead of saying plus a negative 3, I'm just going to write minus 1/3. For my k equals 2, the next term in the list, negative 1 squared is positive 1. 2 times 2 plus 1 is 5, so I have 1/5, positive 1/5. And again, you're going to notice that these sequences end up showing very obvious patterns once you get it going. Now I have, let's see, that was k equals 0, 1, 2, now k equals 3, which would be a negative 1 in my numerator, and then a 7 in my denominator. So instead of plus a negative, I'm just going to say minus 1/7, plus, I already lost track, this is k equals, I should write it down, k equals 0, k equals 1, k equals 2, k equals 3, and then I would have k equals 4 and k equals 5. So 2 more terms, but do you notice the pattern? Looks like we're alternating between positives and negatives, and then it's going with the odd numbers. So this will be a 1/9, I'm just going to cheat, and this will be a minus 1/11. Now that's the expanded form of my summation. You could obviously add those together, but I'm not going to because they didn't want that. And one other thing I want to point out is when you had negative 1 to the k power, that allowed my sequence to alternate from positive to negative signs. So later on we're going to have to develop the general form, and if you notice you have an alternation between positive and negative, we're going to have to employ a similar technique. Moving on. They want us to find the first positive integer of n that will cause this statement to fail. Now there's more than one way to do this, but I like to take a calculator approach. So on my calculator, what I'm going to do is I'm going to clear out my old problem from algebra before. And in y1, I'm going to put the left-hand side of this inequality, so 4 plus n, I'm going to use x, to the x power, and then 6 to the x power. I'm basically just making the calculator do all the mental math I would have to do myself. And I'm going to set up my table, table, to start at 0 because they want positive integers. I want it to change by 1, so that'll give me only positive integers, and I want it in auto mode because I really don't want to do any work. So remember, they wanted to know the first time that makes this statement fail, because for a while you're going to notice the second column, the y2, is going to be a greater value than the y1, but that's only for some cases, because you should notice right here on the integer of x equals 2, that gave equal values for y1 and y2. Up until that point, it was a true statement, but not at x equals 2. And that's what we're going to tell our reader. It fails at x equals 2, and everything after x equals 2. So then, similar question. I'm going to go back to my y equals menu, change my functions. So x squared plus 7x. And then I want to know the comparison between that and 2 to the x power. So again, I'm looking for positive integers, and this time the first column, the y1, is going to be a greater value. Oh, it's not. That's interesting. Technically, I don't know if this textbook says that 0 is a positive integer. I'm going to go with no, but some textbooks differ. So let's ignore 0. Let's say 1 and up. So you'll notice y1 is bigger up until, let's see, gotta keep going. Da-da-da, right there. It fails at x equals 7. Get out of here, calculator. Now that was the first part of section 7.1. If you flip to the back of your notes, you're going to have the second part of 7.1, called part 2, and it's going to ask you to write the general term. Now this takes a little bit of practice, and I'm not good at a lot of things in math, but for some reason this came very easily to me, and I don't know why, but I kind of thought of these as puzzles, and I enjoy this. I'm going to give you a sequence, and I'm going to want you to write the general term, and we'll learn some shortcuts eventually, but for now I just want you to kind of muscle through them. So this is a sequence. Let's assume all sequences start at n equals 1. At n equals 1. So for instance, on this particular sequence, when n equals 1, you're going to get an answer of 5. When n equals 2, you get an answer of 6. When n equals 3, you get an answer of 7. And when n equals 4, you get an answer of 8. I notice a couple things. This is just a sequence of integers, so it's just adding 1 each time. The other thing I notice is that my n equals 1 is kind of an important part. If he is actually already starting off at the number 5, what that tells me is whatever my n value is, on the very first term, I had to add 4 to get to the number 5. So 1 plus 4 is 5. Well, let's see if that works for the rest of the sequence. 2 plus 4, does that equal 6? Yep. 3 plus 4 is 7, and 4 plus 4 is 8. I think we kind of stumbled on the answer right there. We're going to learn in the next lesson that that's a special kind of sequence called an arithmetic sequence, and we'll come back to that later. Now, this guy is interesting. There's a definite pattern, and it's difficult for children to generalize these patterns when they're younger, but you guys are in college algebra, and I think you could figure it out. I have 2, 4, 8, and 16. Those are all base 2 numbers. So, like for instance, this is really 2 to the first power, and then there's some weird alternations of sign. This is kind of like 2 to the second power, except something's going on with my negative, and we'll talk about that. And this is 2 to the third power, and this is 2 to the fourth power to get a 16. And again, the negative sign thing we'll talk about in a minute. In the previous part of the lesson, we had a case of a summation index that had an alternation of signs, and when that happened, what we saw was we had a -1 being raised to a power that was kind of strange. Now, if I just raised it to the nth power, when n equals 1, this would produce a negative coefficient, and I didn't want a negative coefficient. So you have a couple options. What if I did n plus 1? N plus 1, if I take that to the n equals 1 power, if I substitute in n equals 1, what I get is -1 to the 1 plus 1 power. Well, that's -1 squared, and that gives me a positive coefficient. If I think about that for my second term, 2 plus 1, that would be -1 to the third power, which gives me a negative coefficient, and then you'll see they'll alternate after that. So I think this is the right coefficient. And then we discussed earlier that all of these were just 2 raised to some power. Well, conveniently enough, the power that I'm raising it to happens to be the same thing as the number n term. So the rest of this formula is times 2 to the nth power. So -1 to the n plus 1 power times 2 to the nth power. That is not the only general term that I would accept. There's other equivalent versions, but you're going to have to justify them if they're different from me, so just be warned. And then part C, I notice a pattern. I see that everything is, they're jumping through the even numbers. And remember, this represents n equals 1, this is n equals 2, this is n equals 3, and this is n equals 4. So if I want to think about breaking this down into a simpler problem, this is really 2 times 1. This is 2 times 2, and this is 2 times 3, and this is 2 times 4. And the thing they have in common is each one of the nth terms are being multiplied by a 2. So what if we think of this general term as being 2 times whatever the n is for that particular part of the sequence. So 2 times 1 is 2, check. 2 times 2 is 4, check. 2 times 3 is 6, 2 times 4 is 8. Like I said, some of you guys will catch on to this very quickly, and you won't take long at all to come up with a general term, and some of you might have to think really, really hard. So just be prepared. Okay, letter D. Again, I notice that we've got a sequence that's changing or alternating between positive and negative. So I think, again, I'm going to do something weird with a -1 raised to some power. We'll talk about what power it is in just 1 second. Okay, this is when n equals 1, this is when n equals 2, n equals 3, and n equals 4. Now, if I just raise it to the nth power, again, my first term, -1 raised to the first power, would give me a negative coefficient, and I'm not supposed to have a negative coefficient. So to change that, to shift it over by one part of the sequence, if you put an n plus 1, you'll take care of that. And the other thing I notice, besides the 1s in the numerator, I notice the denominators are again going to be the 2's. So this is like 2 to the 0 power, this is 2 to the first power, this is 2 to the second power, this is 2 to the third power. So one thing I notice, besides the 1 in the numerator, in my denominator I've got 2 raised to some power. Now it's not just the nth power, because you'll notice right here in the first term, 2 to the 0 power, my n is actually a 1. So what if I took the n and I knocked it down one level by subtracting a 1? So 2 to the n minus 1 power is in my denominator. For instance, right here, 2 to the n minus 1 power would be 2 to the 2 minus 1 power. Yep, that's a 1. 2 to the 3 minus 1 is 2. 2 to the 4 minus 1 is 3. I think we have our answer. Now, what some math teachers like is they don't like these separations of the terms here. So they'll put the -1 to the n plus 1 power in the numerator, and then 2 to the n minus 1 power in the denominator. And that's a great answer as well. Again, these are not the only possibilities for general terms. You will be able to convince me that yours is correct as well. Okay, more of this. So we have a general sequence, or general term we've defined for the sequence. I'm noticing, so this is n equals 1, this is n equals 2, this is n equals 3. This is base 3 numbers. So this is 3 to the first power, this is 3 to the second power, this is 3 to the third power, and so on and so on. So I think our general term has 1 in the numerator, and then 3 raised to the nth power, because on the first term is 3 to the first power, which is 3. Okay, that one wasn't too bad. Now this is going to be a summation notation series. So that's the thing with the weird sigmas. And you can technically change the index, but what I'm going to do for now is I'm just going to say we're going to start at k equals 1. So if this is where k equals 1, and notice we use k's here instead of n's. So this is k equals 2, this is k equals 3, this is k equals 4, and this is k equals 5. Because this is a finite series, we're going to say it goes up from k equals 1 all the way to k equals 5. That's how you read that notation. And I'm going to kind of change this notation as well. Instead of calling this 0, what if I call that 0 over 1? That kind of fits the pattern a little better, because if you look in the numerator, you see a definite pattern, same thing in the denominator. Let's treat the numerator and denominator separately. If I look at just the numerators, ignore the additions. I have a 0, and then a 1, and then a 2, and then a 3, and then a 4. It looks like it's just whatever the k value is, but 1 less than that. So 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 1 is 2. And then in my denominators, it looks like those are just the actual k values, whatever it is. So if k is 1, it's a 1. If k is 2, it's a 2. So I think that's our answer. Our summation notation, our series written in summation notation, is the sum of k minus 1 over k, where k goes from 1 to 5. Those are difficult. Now we have another alternating series, and we've kind of already seen this before. They want us to start this sequence, it's actually a series, excuse me, at k equals 1, so they're telling us we must start the index there. So let's go ahead and get that done. K equals 1, so this is 1, 2, 3, 4, 5, 6, all the way up to 6. And then if I kind of rewrite this as 1 over 1, I think it fits the pattern a little better. Remember when we talked about alternating series, I know that there's going to be something weird with a -1 in front. And if I just take it to the k power, that's going to give me the wrong sign, because -1 to the first power does not give me a positive coefficient. So I'm going to do k plus 1 power. That'll give me the correct number in my numerator or as my coefficient. And then in my denominator, remember we decided this was k equals 1, k equals 2, 3, 4, 5, and so on. I think the denominators are just the k's. So that one wasn't too bad. But then they get tricky and they say, now I want you to start your index at k equals 0. So same exact series, but this time they want it to be k equals 0, k equals 1, k equals 2, yada yada yada. So this gives me 1 over 1, this gives me negative 1/2, this gives me positive 1/3. Now I don't think the denominator is going to give us much trouble. However, the alternation of the negatives and positives is a little weird. So we have negative 1. If I just raise it to the k power, let's see if that works. So to the 0 power, anything to the 0 power is a positive 1. So that works for that first problem. And then negative 1 to the first power gives me a negative 1. Okay, that works. And then negative 1 raised to the second power gives me a positive 1. I think that's okay then. Now my denominators, if this is k equals 0 and this is 1 bigger than that, what if we put k plus 1 in the denominator? So 1, k plus 1 is 2, k plus 1 is 3. Alright, I think that works. So this is kind of an interesting problem. They gave me the same exact expanded series, but depending on where you started your index, you're going to have a different general term. So I don't know if you find that interesting, but I do. Alright, letter C. Again, I'm going to change this to say 1 over 1 so I can kind of see the pattern a little better. In my numerators, let's forget the alternation for a moment. This is 1, 2, 4, 8, 16. Those are base 2 problems. So this is 2 to the 0, this is 2 to the first, this is 2 to the second, this is 2 to the third, and this is 2 to the fourth. And then in my denominators, these are base 3s. So this is 3 to the 0, 3 to the first, 3 to the second, 3 to the third, and 3 to the fourth. So I see something I can work with here. Let's start with the index at 1, because they told me that, and it goes 1, 2, 3, 4, 5, all the way up to 5. Negative 1 raised to some power will make the signs alternate. Now if I say to the k power, negative 1 to the first power would give me a negative coefficient on my first term, I need to change that because it's not negative. And then next to that in the numerator, I have 2 raised to some power. So I'm going to say times 2. Now the power of the 2's, remember this is when k equals 1, 2, 3, 4. It's not just the k power. It looks to me like it's the k minus 1 power, because that would be 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 2 is 1, 3 minus 1 is 2. And then in my denominator, sorry, I've got 3, and then the same issue going on. I can't just say the k power, I think it's the k minus 1 power. Now that's an okay way to write your summation notation. It's a little sloppy though. One thing I notice is it's okay to keep the negative 1 in front, I don't mind that. But the 2/3 has the same power, so you can actually write it as 2/3 and then the k minus 1 outside of it, like that. It's probably a cleaner way to write that answer. Again, there are going to be other equivalent forms, but you're going to have to justify to me why yours is equivalent. Now we're going to do the same problem, except this time I want your k to start at 0. So 1 over 1 minus 2 over 3 plus 4 over 9. And then this time, this guy is a k equals 0. This is going to be a k equals 1, and this is going to be a k equals 2. So we can kind of cheat and use what we know from the previous problem. If I start at 0, that means we're going to end the sequence at 4 this time. And then, to alternate the negatives and positives, I think if I just take it to the k power, that'll work, because the first one will be positive, because to the 0 power is 1. And then to the first power is negative, to the second power is positive, and so on and so on. Now for the 2 and the 3, I think they're just taken to the k power. So, I know they're just taken to the k power actually, because 2 squared is 4, 3 squared is 9, I'm just checking this last term here that I wrote down. This is definitely not the most simplified version of this summation index. Since everything has the k power, you can actually simplify it to say negative 2/3, I could put the negative 1 and the 2/3 together, to the k power. But either one of these are equivalent. If you don't feel comfortable condensing it like that, I'm okay with that. these take some getting used to, so you're going to have a lot of practice with this. We're going to learn more about special types of sequences in the next section, but I do appreciate the difficulties that are associated with this lesson, so try your best.